It's going live now, and I set it to public. Let's hope to God that it stays public this time. Okay, yeah, this is fine now. Awesome. Okay, great. Okay, so good morning again. My name is Akintayo Jabar. You can call me Tayo. I work as a data scientist at Nifio. This is an AI-enabled climate financing company. I work on building models to help with alternate credit risk assessments in the solar home system space to address the energy deficit problem in Africa and some other parts of the world like Southeast Asia and the rest of the world. So this week we'll be looking at relational data, that is data regarding databases. And I guess I'll start now. Just start sharing my screen. So what can you guys see right now? For some reason, technology is doing me something else this morning. Correct? Okay, awesome. Thanks. Sure. All right. So like I said, we'll be looking at relational data today for week 4. A quick recap. Last week, we looked at data collection and the different data formats that we have. And if you remember, one of the listed data sources was data from databases. So where you use like database queries to obtain data. So now we're taking a closer look at that kind of data, and they're typically called relational data. So the outline for today's class is going to be looking at a quick overview of what relational data is. Then we go to entity relationships. Then we look at how to manipulate relational data. Nothing too deep here, just the basics. And then we look at what joins are, because they're a very important subtopic in dealing with relational data or data in general. Okay, so our first subsection would be relational data. Now, if you have any questions or concerns, you could drop them in the chat, or you could just pull my attention before we continue. Okay, so a quick overview of what relational data is. Now, relational data it clearly comes from the keyword, which is relation, showing some sort of connection between different entities. So the idea is relational data is a collection of organized, interrelated data. But the best way, the way that relational data goes about arranging this or displaying this or bringing it to life is in a tabular structure. So where you have a table, and then in the table, you have rows and columns. Now, we all know that rows are horizontal and columns are vertical. Well, I'm assuming that we all know, but if we don't, it's a tricky thing. rows horizontal, columns vertical. And now each row represents a record. If you would go further in the record, it is represented as a tuple, or better yet, you call it an observation. So if you keep going deep into data science terms, a row is regarded as an observation. Now, what is unique about a row is that it contains total information about an entity. I've just used another keyword, entity, but bear with me. We're going to look at it in the next section. So when you take out a row from a table, the expectation is that it gives you all the information you need about a particular entity. So if you have, for instance, a customers table, every row should be about one customer. So if I take a row out of a table, it should give me all the information about that customer, at least all the information available about that customer. Meanwhile, a column is regarded as a feature or an attribute. So what this means is each column, each field contains a special attribute about that row. So if you take a row out, a row of customers, for instance, you have their first name, their last name. There's a column known as the first name, there's a column known as the last name. That column last name is a special feature for the customer. It gives you information about one thing about that customer. So that's what a column is. So I've been talking in abstract. Let's look at what it actually is. So just to continue my explanation, now this is a sample table, right? A sample table, let's call this customer table. Now, you can see the first row here is the header, because for every table, you need to have the header, right? So we have columns, ID, first name, gender, email, and profession. Now you can see that this is color coded. So the yellow color, we have the green, and we have, oh, did myself, I don't even know what color this is. But we have this thing that looks like purple, right? So the green color is what you call a row. So everything that goes horizontally is a row, but I color coded this one just to highlight one row for you. So now, according to what I was saying about what a row is, it gives you all the information. Thank you. It gives you all the information that you need to know about a particular record or about the entity on that row. So if we look at this row, this green row, we can see that the ID is 103. The person there is Tejumade Afonja. She is female. This is her email. And this is the profession that she belongs to. So you can see that once we take out 103, we've taken out everything about Tejumade from this table. It is a complete collection of info. That's what a row is. Meanwhile, if we look at what a column is just one field. So this field is the profession's column. We have so it shows us all the different professions. So Tayo's profession is 301, Kenichi's is 302, Teju is 303, Fola is 302, then Zazu is 304, right? So this is just one particular information about everybody here. So if I took out profession from this table, you realize that I still have some information about everybody on the table. So that's what we mean by a column is just a unique field. It's just one field that gives partial information about the record. Now, for our magenta column now, which is the ID column, it is what we regard as a primary key. Now, what is a primary key? A primary key is a column of feature that is unique for every record in a table. What this means is no matter what is happening, even if there is another person that's going to bear Tayo, Jabar, and we want to enter them into this table, they have to be a separate record. That is what tells you that the second Tayo Jabar is different from the first Tayo Jabar because the ID is unique. No two records can have the same primary key, can have the same value of the primary key in a relational table. Do you understand? So that's it about rows, columns, and primary keys. Do you have any? So now, a little more on primary and foreign keys. We already mentioned in the last class that, in the last slide, that what's it called now? A primary key is a unique column, a column that is whose values are unique to each of the rows in the table. So now what is a foreign key? Let's look at these two tables, for instance, right? Let's look at them closely. We have the customers table, which is the same table we saw in the previous slide. We have customers, we have 5 customers in this test table, and we have their professions here, 301, 302, 303, and 304, right? Now we have a separate table known as a professions table. Now in this table, the table has its own primary key as well. 301, each of this code corresponds to a certain profession. So 301 is a doctor, 302 is an engineer, 303 a professor, and then 304 is a mechanic. So what does this tell us? Ordinarily, reading this table is going to tell us that Tayo is what? Profession 301, doctor. Kenichi, profession 302, engineer. Fola, profession 302, is also an engineer. And this guy right here, 304, is a mechanic. Are we seeing something play out here? So now you realize that we were using this code to actually, we're using these codes here, these IDs, to decode what profession each person here belongs to in this professions table. So now that explains what foreign keys are. Now a foreign key is a primary key in one table that is then used as an identifier in another table. So in this professions table, the ID column, the IDs, which are 301, 302, 303, and 304, they are primary keys in this table. But then what are we using them for in the customers table? We're using them to identify professions of the customers, making them what? A foreign key in the customers table. So that's the explanation here. The ID column in the professions table is a primary key here. But then the professions column in the customers table is a foreign key, identifying the professions in the customers table. So now think about it like this. I mean, majority of us here are Nigerians, or majority of us here, we have our one country. Now, whenever we see someone else from another country in our space, in our country, what do we call them? Foreigners. So you can see another thing about what I said, naming in computer science, everything makes sense. So if you're a foreigner, it means you are somewhere that you do not originally belong to, which is what a foreign key is. This foreign key, the original home is a professions table where it is a primary key. But now when the professions carry their two left legs to another table, they become what? Foreigners. They become foreign keys. Do we understand? Okay, great. No reaction. So now another context, so another concept that we want to explain is indexes. So now, not to be confused for indices, this is indexes. Now, what is an index? An index is a database structure that helps us to speed up the time to complete a search within a database. Now, this index table, an index table is then a separate sorted table. Now, it is in quotes because you are not the one that creates the index table, right? But what it does is it holds the location of records within a table. Now, bear in mind that this is for illustration purposes, but this is the way it is represented in a computer memory. So let's look at this table, the customers table again, right? we have the following fields: ID, first name, last name, gender, email, and profession. Now, if we were to represent this in the computer system, each row, each record is going to have an allocated memory location. So let's assume that this is the way the computer allocates its memory. Say record tile is in 100 and so forth. So 100, 200, 300, 400, and 500, right? Now, this is the customer table. This is the table that we created by ourselves. Now, after doing that, the computer then creates another index table, so to speak. What it does is it could take a particular field in this customer table and then point to its location in such a way that it is sorted. So you could take a particular field. So what this means is we have this index table for the last name, right? We could have another index table for, say, emails. Do we understand? So it takes the last name, for instance, it sorts all the records in the last name column and then points to their location, such that when you then go to that database, or when you go to this table and you want to search for something, the first point of call, rather than going through records 1, 2, 3, 4, 5, if, for instance, wanted to look for Ducor, now, want to search for Ducor here, the way it works is the system is first going to direct itself to the index table, identify where Ducor is, location 200. Now, once it knows location 200, it is no longer looking just for Ducor. Rather, it is looking for the location 200, and it is going to understand where the position 200 is within the system, rather than looking for Ducor in a list of many names. Does that make sense?
Yes, it does.
Thank you very much. Okay. So I guess we're done with section 1. So first things first, our first quiz question, what is a relational database? Let's do this same way we did it the last time. We answer in the chat. Thank you. Okay, people are following. Nice. Okay. So yeah, a relational database is a database that uses tables or a tabular structure to store and organize data. Question B, what does a primary key in a relational database represent? Awesome. So yeah, the primary key in this relational database, what it does is it is a unique identifier for each row in a particular table, as we have seen in the previous slide. So I guess we can move to the next section. We haven't done too much. So after the next section, we're going to take a quick 5 minutes break before we then move on to the next one. So we can move to entity relationships now. So in entity relationships, we are going to be discussing what an entity is and how different entities could relate to one another. Now, one thing that I want us to recall is I mentioned something in the previous section when I said each row in a table is a separate entity, right? Sorry. So first and foremost, whenever you have a database table, each row is an instance of what that table represents. What does that mean? If you have a customers table, then each row is an instance of customers, meaning each row is a customer. Now, that instance is also what you refer to as an entity. So each customer in the customers table is a separate entity. And given the fact that whenever you're creating a database table, or best practice for creating a database table is whenever you create a table, you are referring to a real life object or a real life concept. So we understand the concept of customer. We understand the concept of sales. We understand the concept of professions. These are all real world entities. So that's what an entity represents. An entity is an instance of a real life concept. So now, in the context of databases, how do these entities relate? Basically saying, how the two tables, how can they be interconnected? So there are three main relationships that can be defined for entities. We have the one-to-one, we have one-to-many or many-to-one, and then we have many-to-many. So the first one that we're going to be looking at is the one-to-one relationship. Now, what does this show? This shows an exclusive or strict case of one record in a table only matching another record in a second table, meaning when you have table A or table B, entity A in table A is only going to match one entity in table B. So entity A strictly matches one entity in table B. That is English. Let's look at it properly. So now if we look at this customers and usernames table, right? So we're assuming, for instance, that this is an e-commerce situation, right? So where you register to be on to use their service online. So say ShopRite had an e-commerce interface. After you register, then it gives you a username, right? So let's assume that all these customers have registered on the ShopRite website, and then they've gotten their usernames, which is this. Now, what the one-to-one relationship is telling us is that every customer should strictly have just one username. Think of it like this. Whenever you are subscribing to, or whenever you're registering on a new platform and they ask you to enter your username, once you enter a particular username, say one that is common, what's the message you usually get? You'll be like, this username is not available, or you cannot use this username, something along that line. That is them in a way enforcing a strict one-to-one relationship, saying that every customer should only have a unique username to them. So meaning Tayo Jabar is only going to match username Tayo Jabar in this table. This Tayo Jabar cannot be Tedra Fonja. Thank you. Username already exists and so forth. So this is an example of a one-to-one relationship. So I hope that is clear. It's very simple, one-to-one. Only one customer can have one username, and one username here can only be used by one customer in the customer's table. That is the one-to-one relationship. Now, the one-to-many or many-to-one relationship. Now, this is for a case where a record in one table could match multiple records in another table, or multiple records in another table could actually be related to just one record in another table. Let's explain. Now we go back to our profession and customers table, right? So now we know that there are 4 finite professions according to our table: doctor, engineer, professor, or mechanic. Now what this is telling us is that this profession could be held by many customers, meaning multiple customers could be a doctor, multiple customers could be engineers. You could have more than one customer being a professor and more than one customer being a mechanic. Now, this is an illustrative table, but we have a case where we have more than one customer being of the same profession. And what is that? 302, engineer. So according to this, Kenichi and Fola are both engineers. You can see how one engineer can match 2 in this table. It could be 2, it could be more. Do you understand? And it is also showing the reverse, which is multiple customers could match a single profession in a profession table. This is a simple case of the one-to-many, many-to-one relationship. And then for the big guy, which is a big case, many-to-many. Now, what does this tell us? This is showing us that there's a possibility of multiple records in one table matching multiple records in another table or vice versa. A simple way to interpret this is, given this examples that we have, customers and items table, what this is trying to tell us is that many customers would buy multiple items, meaning that customers Tayo and Kenichi could both buy tissues and samosas. Also saying that the tissues here, or samosa, could be bought by multiple people here. I could buy tissues, samosas, and pens, and samosa is bought by Kenichi, Teju, and Fola. Do we understand? That's a case of many to many. But now I can start to see the complexity in this kind of relationship, because how then do we represent this in a database, given that one of the properties of databases is that for every record that you want to have in a database, it has to be uniquely identifiable. So if we have Tayo buying tissues, right? And then Tayo comes again and buys samosa. A crude way to do this would be saying we want to have the customer's name, and then we have a column for the items bought. So customer name, items, item 1, item 2, item 3. That is a crude way, because what that means is for every time you want to add a new record, you need to alter the structure of the database by adding a separate column all the time. It is not advisable. It's more computationally expensive, and it's just all around bad practice. So this brings to fore a clear conundrum, and it has to be sorted. So in comes what we call associative tables, right? So this is how it works. You can break it down. You can break your many-to-many relationship. You could break it even further by introducing an associative table, right? So what it is basically telling us is that you could write the relationship such that for your entity A, it could match multiple records in your associative entity, and multiple records in that same associative entity could match a single record in entity B. Let's look at a proper example for that. So now, in the case of customers and items, we are looking to introduce this associative table that is going to bring both of them together. Okay, so Olatunde is asking a question here. For one-to-one relationships, what scenario do we decide to separate all the columns from another table as against the same table? Okay, thanks. This is why it's good to have champs on the call. Thanks for that. Yeah, exactly. I didn't want to bring the whole idea of normalization to this class because first, it's not an intensive database class, but yes, normalization is what informs the level of breakdown that you have in your table, helps to work with the separation of entities to very close to exclusive appearance in your database. So thanks again for that, Paula. So to move forward, the customers and items table. Now, our associative table here is going to be an items bought table or a sales table where we hold information about the customer and the items they have purchased. Now, keep in mind, you notice that this table looks like a table for only codes. That is the whole idea of associative entities, because what you're trying to do is make sure that each record or each row within this associative entity would show you what entity in table A and what entity in table B are interconnected for that record. So basically what you're getting here is for sales 1101, customer ID, customer 101, Sorry, I didn't update this. Customer 101 purchased item 531, right? So that is a sales record. It's a separate sales record. We also have sales 1102, where customer 102 purchased the same item 531. Now, because they purchased the same item doesn't mean they are the same action or they are the same transaction. Rather, what makes them unique is the fact that this is customer 102 buying 531 and customer 101 buying 531. Same thing here. We're seeing customer 103 buying 533, which is pens. Same customer 103 buying 534, which is airports. What that tells us is customer 103 has bought two items here. Next is 104 buying 532, then 105 buying the same item 533, and then customer 102 coming back to buy airports again. So we can see that with this associative table, we can clearly distinct what the customer is and what item they've purchased. It is still showing us a many-to-many relationship because you could have the same customer appearing multiple times in this table and also have the same items appearing multiple times. But I have just explained that the uniqueness of this table is a combination of features, meaning a feature from entity A and a feature from entity B. And when we're talking about you being from somewhere and going elsewhere to stay, that's the concept of a foreign key. So meaning that entity A has to be a foreign key in this associative entity, and entity B also has to be a foreign key, hence the codes that we have. But together in the associative entity, they form what is called a composite key. So now you have primary keys, you have foreign keys, and you have what you call a composite key. Now, a composite key could be a combination of more than two foreign keys, but it is essentially a case where you have more than one key, usually foreign keys from different tables, being used as a unique identifier in another table. So in this case, an associative table. Does that make sense? Do we understand this? Okay, so I'll take no comment or question as yes. Then we can go to our next quiz. So let's use this to jog our memory of what we have just learned. So now question A, what does an entity represent in entity relationship modeling? Thank you, Bilkis. We can answer this by same way. Question options in the chat. Okay. I saw a C. Okay, yeah, it's clarified it now. Okay, so yes, that is what an entity is. An entity is an instance of a real-world object or a concept. So something that is tangible or something that you can relate to. That's the whole idea, because that is what is going to inform how to understand how to work with these quantities. So apart from the fact that you're just saving it in a system, if you are going to build a solution using a database, you need to be able to conceptualize it properly such that when you want to build features for whatever solution, you know how to interact with the database object. So an entity has to be a real world object or a concept. So for question B, which of the following best describes a foreign key in entity relationship modeling? Exactly. Exactly. So I guess we're all following and there's no confusion. That's amazing to see. Yes, so a foreign key in entity relationship modeling is definitely a key that is used to establish relationships between the entities, as we saw in this case. All these two became foreign keys just to establish their relationship. We have two more questions. So in a many-to-many relationship, what is typically used to represent the relationship in a relational database? Christopher, sorry, please. Let us finish the class, then you can continue drawing. I see you're using the annotation tool. Thank you. Okay, great. So I don't know if there is a confusion between question C and D, but I think people are mostly answering question C. And yes, the answer is B. To typically represent the relationship, you have to create a new table that connects both entities. But yes, you create a new table and then you introduce a primary key in each of the related tables as a new foreign key there. But the answer is actually a new table that connects the two entities. And then for question D, what is an associative entity in an entity relationship diagram? This is great. I like this. I like what I'm saying because this was supposed to be like the most complex part of entity relationships, but I see it's not a problem for us. Love to see it. So yeah, an associative entity is an entity that connects two or more other entities. So amazing. At this point, the time is 11:43. Let's reconvene at 11:48 for the next section, which is on manipulating relational data. But in the meantime, please don't forget to fill the feedback form as well as the attendance form. And also, if you are yet to fill the group preference form that was shared in the beginning, and if those links can be reshared again, please let's take the time to get them filled. We'll be back in 5 minutes. Okay, I guess we're back, and so I'm going to go first things first. There's conversation going on in the chat, and the first question is, can you please give additional examples of many-to-many relationships to drive on the concept? Okay, so that one is simple. So take, for instance, students, right? When you're in school, you take multiple classes, correct? So as a student, so say you're in uni or secondary school, it's very simple. In secondary school, before you did WAEC, you were taking 9 subjects, correct? Now, those 9 subjects were taken by, let's say your class was 40 students. So those 9 subjects were taken by 40 students. Do you see where I'm going with this? A student is taking 9 subjects. Each of those 9 subjects was taken by multiple number of students. That's another case of a many-to-many relationship. Does that make sense? Olatunde. So that's one. Then 2. Now, okay, so does anyone have an example of where you may need to duplicate the data multiple times? I'm not very sure I have context, but the idea of having separate tables or normalizing is such that first, each entity is easily identifiable by their separate tables, right? And then it becomes so easy to collect data from as many tables as possible when you need it by simply using joins. So I don't know if that answers. So if you have to duplicate data in a table, then that table is not perfectly normalized. Do you understand? Like if a single record is appearing multiple times, and now keep in mind when I say record, I'm not just saying maybe one customer is appearing multiple times. I'm saying record, meaning the entirety of that row is appearing multiple times. Then that table is not properly normalized. Thank you. All right. Awesome. I like this. I like this. I like this. Okay. So thanks guys. Welcome back. We're going to be moving on to the next section now, which is manipulating relational data. So now we've explained the concept of it, the idea of dealing with data in rows and columns. So now, how do we manipulate relational data? Now, keep in mind, these two are not exhaustive. This is not an exhaustive list, but this is what we're going to be covering in this class. So Pandas and SQL Light. I mean, with Pandas, there's and even a senior brother to Pandas, which is like Spark by itself, or some other packages that you can use to do the same or similar things that Pandas does. And then you also have SQL Lite. I mean, this one goes without saying. It is an SQL system for managing relational data. Now, that said, this is SQL Lite. There are other, what's it called? There are other management systems that use SQL as well that can handle relational data. So you could have SQL Server, MySQL, TransactQL, PostgreSQL, and so forth. But let's move first with Pandas. So what is Pandas first and foremost? Pandas is a Python library that has tools for easy manipulation of data. Now it has tools that can create the idea of your data existing as rows and columns, like we have shown in the previous slides. So what that means is, originally, your data is not stored as rows and columns, but when you use Pandas to manipulate your data, it could help you create a data frame, which is another name for a table, such that you can then apply the principles of dealing with rows and columns on that data frame. Okay. So this is an example, right? And keep in mind, we are looking at Pandas and SQL Light in the context of within Python. So that's why our code snippet is in Python. So the way to call Pandas in Python is import Pandas as PD. It's very short. So import Pandas as PD. Then once you have imported Pandas, you can then use any of its available methods to create a data frame. So this is a simple example of using Pandas to create a data frame. Now, remember I said each row of a table is known as a record or a tuple. So here we're using multiple tuples to create a data frame. So we have tuple 1, 2, 3, 4, 5, 6, and then we specify the columns. That's the name of the columns. We use it to create the data frame. So once we run this and then we call the data frame, then we have ID. This is what it gives us, the ID, last name, and the first name. This is what a typical data frame looks like when you create it using Pandas. So to continue this, let me just point out something here. You can see these two, the first two columns where you have 0, 1, 2, 3, 4, 5, and then you have 1, 2, 3, 4, 5, 6, right? So now, this ID is what you would typically refer to as what? Your primary key in a table. Is that correct? This is your typical primary key, the ID, right? But now what 0, 1, 2, 3, 4, 5 is what you call a positional index. Now, given that we're familiar with computers, we know that counting within a computer system or within the context of our work usually starts from 0. So that position 0, position 1, position 2, 3, 4. In fact, we adopted that with our style during this course. We started with what? Week 0, week 1, week 2, week 3, and so forth. So that is what you call positional indexing. It is different from what you would typically refer to as your primary key. Now, keep this information in mind while I show you the next set of examples. So an easy way to manipulate, to extract data from your data frame is using the lock and ilock commands, right? So now with lock, you could directly call for a particular record. So you say print location 1, the item in location 1, I want just its last name. And it's telling us that that's Coulter, according to this table. ID location 1, last name, Coulter. Simple, right? So the same thing, location. Now, whenever you have this colon in Python, so now I'm just going to refer us back to the Python refresher class, because this is a notation that I believe must have been covered when we're talking about slicing a list or something. So whenever you have this colon in square brackets, what you're saying is, I want everything, all the rows, I want everything. So I want all rows, but I only want their last name. So the last name for all rows within this data frame. And that's what gives us Coulter, G, Lee, Mani, Gates, and Musk. Just for reference, Coulter, G, Lee, Mani, Gates, and Musk. And then if we wanted to, so now this third one, you can see that when it returns the solution, or when it returns what we query for this second command, it only returns the ID, right? It doesn't give us this, doesn't give us a column name here. Do we get? And that is because whenever you query a Pandas data frame, it doesn't do anything in place. Rather, it just gives you a copy of what you ask for. And it is even more notorious when you call for a particular column, it only returns what is called a Pandas series. Now, a Pandas series is just a single row without, more or less without structure, right? So that's why you just have the ID and the names. Now, if you wanted to return the same command, but make it return as a data frame, which is structured, you just have to, all you have to do is include this last name in its own square bracket. So you introduce another square bracket, and that prints out what? It gives you the data frame. It gives you a data frame structure. So you have the ID and the last name as a column here. So now this last two commands are ilock and lock. So what did I say the ilock was? So now the ilock command is based on the zero indexed positional counter. So it's like I was saying, week 0, week 1, week 2, as in a computer, as we can see here, 0, 1, 2, 3, 4, 5, right? So now, based on the indexed, the zero indexed positional counter, you can then call the ilock command by specifying integers in both positions. Now, look at lock. We're directly providing the column name that we want. But with ilock, you have to use integers, right? So now if I say I want I location 4, that's the item, that's index location 4 in column position 1. So usually when you have square brackets or tuples, it usually goes XY, which is rows and columns. So I want row 4 in index location 4 and row 1 index location 1, which is 0, 1, essentially the second column. And let's look at how that plays. When we print that, it gives us bill. Let's confirm. Given this table, the column position is what? 0, 1, 2. So, sorry, it takes the ID as a primary key, right? So 0, this is 0, 1. Do you get me? Yeah, 0, 1. Then now index location 4, which is 0, 1, 2, 3, 4. What does it give us? Bill. Does that make sense? And then when you do the same for lock, that's location 4, and the last name, what does it give us now? It uses the primary key, which is what the location function does. It uses the primary key. So it goes here 1, 2, 3, 4, and gives us what's the last name? Mani, which is Mani here. I hope that makes sense. Was that clear? Okay. All right, thank you. So now that's for Pandas for now. Now with SQL Light. Now what is SQL Light? SQL Light is a relational database management system, otherwise known as what? RDBMS. Yes, I agree, Tedru. I agree. The location and iLocation, index location thing could be confusing, but yes. So SQLite is a relational database management system called an RDBMS. So now what is a management system or a relational database management system? In this case, we've been talking about relational tables, right? That's typical customer table professions and all. But when you now have a suite like an ID, one big system that manages databases. So you could have multiple databases, a system that can manage all of that and then give you the capability to manipulate those databases in line with the principles of relational data. And that is what is called a relational database management system. So SQLite provides you that. Now, what is one of its unique features? I feel like this is its most unique feature and its strongest selling point. With SQL Lite, you don't need a connection to a server. Now, when I was listing some examples of systems that were based on SQL, you would notice that I mentioned SQL Server, MySQL, which also has a server, Postgres also has a server, Oracle also has a server. Like every other form of SQL manipulating or SQL RDBMSs, they are server-based, meaning you need to have a connection to them before you can then access the database. Meanwhile, with SQLite, you will have a separate, a single database file, and you connect directly to that file. What that tells us is it is light. Now, I play on words here, right? It is light, hence light. It is light, and to even take it further, you have SQLite present on the edge. Now, what do we mean by on the edge? It simply means on every device. So now for the other servers, you need to be deliberate about having them on your machine. You install the server, then you can interact with those SQL, with those several servers, or you connect to some remote location to access those connections. But with this one, every device. Now, SQLite is the most popular SQL RDBMS at the moment that is currently in use. So it means if you take up your phone, it's your phone, there's SQLite on it. If you say you don't use iPhone, you use Android, there's SQLite on it. You have SQLite on the edge. That's what you call on the edge. Every like hardware device, SQLite is present there. There's SQLite present on your laptop, whatever you're using right now. SQLite is present there because it is light and has been adopted as a, what's it called? A form of standard to write information within your devices, to the point where it is not only SQL information or database information that devices use SQLite for. If you are going to write XML or read such files, the SQLite presence on your devices could help with that. So that's its strongest selling point. Also, if you were trying to build a system now, you're trying to build a solution, and you're thinking of using a database. Now, usually, or in the past, you had to spin up a server and start connecting. What if the day you're doing the demo, NEPA decided to build there, or internet decided that I'm not going to work? Then you see that your connection is breaking. That's if you have a remote location. But with an SQLite database, you could have the file sitting on your machine, and then your demo is going to move smoothly. So those are some of the sweet advantages of using SQLite. I mean, of course, it uses SQL. SQL stands for Structured Query Language. Now, transactions maintain the ACID properties. Now, I've said all of this, but just to reiterate that with SQLite, you are not losing any of the properties, or you're not losing any of the features of having relational databases. And the main properties of relational database are acronymized to the ACID properties. So atomicity, consistency, isolation, and durability. Now, what does atomicity mean? It means an action is that one action. So when you have a transaction in a database, it either happens or not. The fact that it happens does not affect another thing. So if it happens, it has happened and it has finished happening. It doesn't, because it happened, affect something else. So it is atomic in that way. That's what you mean by atomicity. It stands on its own. One transaction is one transaction. The transaction either happened or it didn't happen. So nothing changes in your database. It is consistent, meaning your data is consistent. I think that one is really straightforward. Like, you carry out the transaction here. If you carry it out today, you carry it out tomorrow, you're going to get the same results, or you're going to see the same thing in your database. Now, it is isolated. What this means is, once you're carrying out a transaction on a particular record in your database, that transaction is isolated from any other person probably using the database, meaning that your result is not going to be affected by someone else's result. Do we understand? Or by someone else's action. So another transaction is not going to affect yours. That's what you mean by isolated. And then durability. What this means is whatever transaction you have carried out, right? Whatever change or whatever action or whatever the result of that transaction, it is going to be the same till kingdom come. So regardless of whether you have a system failure or someone moved your database file elsewhere or something, your transactions result is durable. It returned A, you come back in 100 years, that same transaction returned A. It doesn't change. So that's what we mean by the ACID properties. I know it is rough and it is quickly breezed through, but I just wanted to mention that those are the strengths of SQL Light. Okay, so now how do we use SQLite in Python? Very simple. There's an SQLite 3 library. Now, keep in mind that this package is usually subject to versioning because it's an open source package and they're making updates to it. So just always have that in mind, right? So the first thing you want to do is establish a connection to your SQLite package. Once you have established the connection, you then create a cursor object. Now, cursor object is basically saying you are, how do I illustrate this? It's basically like an instance of your connection, right? That you can then use to execute or to carry out actions on that connection. So what that means is, the reason why I said you can use it to carry out actions is that you have verbs like methods like execute, commit, rollback. Thank you. Instantiating your connection. That's what I said, an instance of a connection object. So that's what your cursor is, right? Now, an example of this is, so keep in mind that whenever this is just a rule of thumb, whenever you open a connection, you always have to close it when you're done. Otherwise, things could happen. Things that are peculiar to your system, to your whatever you're working on. But it's always advisable to close a connection when you are done with all of your database operations. So a simple example for this is we want to create a table now, right? So we call the execute command, the execute method, the execute function of the cursor, and we ask it to create this person. Now, when you're creating database tables, you specify the, You specify the column name and then the data type. You specify the column name and the data type. Now, if there are other properties of that column, you just enter a space and then you put those properties. Now, in this case, we want our ID to be our primary key. So we enter it as what's the primary key. Our last name is going to be a text. It's going to be of the text data type. First name, text as well. We close that. So this command is basically saying, I'm going to take an SQL statement and have it wrapped within my Python, statement. So the same thing, I want to create another table called grades, where we have the person ID as an integer, and it is also going to be our primary key in that table. Then you have homework 1 grade, integer, homework 2 as an integer as well. So we've just used SQLite within Python to create 2 tables. Now, after you do that, you commit. So commit is like saving the whole operations on the connection object. So you commit this. Is that clear? Awesome. So this next slide is basically just showing how you then populate that table. So remember, we created a table person. So Olatunde, this line here, con equals SQLite 3.connect database.db. Now, this question is showing that you're probably familiar with connecting with Postgres and other server-based RDBMSs. So that's what I was highlighting as the strength, one of the strengths of SQLite, of SQLite generally. You can connect directly to a database file. So there are no other details but the database name. The only other things that might be here might maybe path to where it is contained, but otherwise you connect directly to a database file. You can do that. Do you understand? So remember, we created a person table with columns ID, last name, and there's someone who is in this meeting. All right, awesome. Yeah, so we have columns ID, last name, and first name. So this is how you insert into those tables, right? So you insert into table name values, provide the values as a tuple, right? So we want to enter 1, quota, and Zico. Now keep in mind, we said our ID column is what? An integer. Our first name column is a text. Last name column is a text. Now, texts are strings, right? Hence the use of the quote. The table name is here. Create table person. Create table grades. Is that clear? Thank you. So now when you want to insert into the table, you then go insert into table name, which is person, right? Insert into person values this, insert into grades values that. So those are the simplest forms of command that you can execute in SQL: create, insert. So now the almighty one, which is what we as data scientists or we as data practitioners most of the time would be doing, is reading data most of the time. And to read from an SQL table, an SQLite table, you typically follow this template, which is you select a certain number of columns, or you select certain columns from what tables, so more than one table, possibly one or more tables, where you specify some conditions. So I'm just going to show you how to read from an SQLite table using just two methods basically. So now this one is for, say you're writing a system that is pulling data from somewhere, maybe a data pipeline, so to speak, and you're not using Pandas at that point. So this is just within Python directly, right? So you're saying you could just call for each row in cursor.execute, select all from person. So now this is the command that you're running, select all from person. Now, when you run cursor.execute, select all from person, it is going to return everything you have in the person table. Now you want to loop through that result and you want to print each item there. So that's what you have here, print row. So for each row, print it. It's going to print these one by one. 1, 2, 3, 4, 5. That's everything you have in the person table because that was what we created back here. Now we could do the same thing using Pandas. And remember, like I said, Pandas gives you the ability to present your data looking like your typical relational data, like a typical table, which has rows and columns. So here it's returning the rows as your raw tuple. Meanwhile, with Pandas, you can use the read SQL query command and then select all from person. You specify the connection because this connection is connecting towards to your database file. So you need to specify the connection and also indicate the ID, the index column for that table. Now you could include this parameter or not. It depends on you, right? So, but if you wanted to specify the index, you specify the index of the ID. Once you run this is the result. It's going to give you everything you have here as a table and also including what the column names as well. Is that clear? I'll move to the next slide. Okay, so it's 11:20 now. We take another, sorry, yeah, 11:20. That's referring to West African time. We return at 11:25, and then we'll look at the last section, which is joins. Yes, the slides have been shared on Discord. They are going to be shared again. But in the meantime, while we are taking our break, please do not forget to fill the feedback forms, the attendance form, the group reference form. I'm sorry we are loading you with too many forms to fill, but please bear with us. I mean, we're all here doing data, and data is going to help us to make the most effective decisions. This is a clear use case for the work that we are doing. We're collecting data and we're using it to serve it better. So please fill our forms so that we can be better at what we're doing. We reconvene in 4 minutes. Okay, we're back. Oh, welcome back. Our final section for today is joins. Now, what do we mean by a join? I mean, I always say these things, and it feels like I'm overflogging it, but this is why I like the way things are named in computer science. Because what is a join? What do we know as join? Join is you bring this one, you bring this one, you put them together. That's join. And that's what it is. Just joining two things. But in this context, it is how we join our entities or how we join. Oh, that's also join too, yes. But the Lord is not joining anything here. So yeah, that's what joins are. How we join or how we bring together different entities within our workflow. So now in doing these joins, we have four main types. Now I said four main types because again, this is not an exhaustive list, but more often than not, these are the kind of joins that you'd mostly encounter. We have the inner join, the left join, the right join, and outer join. In some places you'd see cross join. In some other places you see anti-left join, anti-right join. All those ones, they are complex. But the other thing is they are based primarily on these main types of join. So if you say an anti-left join, it's practically saying what is the opposite, what's the transpose, what's the flip side what you get when you do a left join and so forth. So these are the four main types, and so we're going to be discussing today. So now, pardon the quality of this image, but I believe we can still see it. This is just a rough overview of what joins are. Now, the first one is inner join. Using this Venn diagram, basically. I mean, if we still remember how to interpret Venn diagrams, we know that this place is what intersection. And intersection is what is common between this circle and this circle, right? So that's what an inner join is. It means you join these two tables based on what they have in common. And now if we're talking about tables, what do they have? Columns. You don't join by rows, you join by columns. So you're joining tables A and B based on the columns that they have in common. That's an inner join exclusively. Wow. These are some really nice nerd puns being put together here. Okay, so that's inner join. Then left outer join or left join. Now forget the old outer that comes after right and left. They always put it there, but don't worry, it's still a left join. Now what is a left join? A left join is saying I want everything in the left table. Now we know left, we know right. Don't look at my image here because it's a mirror image. So my left is looking like my right. But when you're looking at something, you know where your left is, you know where your right is. Left join is saying, I'm keeping everything in my left table and the things that are common to my left and right table. So if you look at this image, we're keeping everything in table A and what is common between table A and B. So it's the blue portion that gets returned in your left join. For your right join, you do the flip side. You keep everything in your right table and what is common between your right and left tables. And then for your full outer join, we're taking everybody. We're keeping our left table, we're keeping our right table, and we're keeping what we have in both cases. So that's what your full outer join is. That's a quick overview. Now, the next slide we'll be looking at how to achieve these joins using Pandas and SQL. So remember we created two tables in the last section, the person and grade table. Now, these two tables are going to be our, what's it called now? Our guinea pigs. These are our test tables, right? Table person, table grades. just keep in mind, if we need to refer to them, we'd always go back. So given the following tables, let us join them. So first is inner join. So inner join, we are going to show you how to do that using Pandas and how to do that using SQL. Now, if we look at the two tables first and foremost, and we want to join them based on the ID, right? We are looking for what is common to both of them. So if we look at this, can someone just like tell me in the chat what rows you think are common to both tables? Let's try and make this interactive as well. Yes. So ID and person. Yeah, that's fine. Now those are the two common columns. But I'm talking about in the records, the rows that are common to both tables. Thank you. Someone says rows 5 and 6. Exactly. So we're looking at rows 5 and 6, or rows with IDs 5 and 6, and person ID 5 and 6 in both tables. So now when we are doing this join, we're expecting to get all the columns in, because the columns are going to be returned, all columns will be returned, but the records that we're going to get is the rows that are common in person and grade. So we are going to get a return of last name, first name, homework 1 grade, and homework 2 grade, as well as person ID. But we expect to only see Gates, Bill Gates, 58595, Elon Musk, 80 and 60. Once we get that, then we know Pluto is active. So how do we do that in Pandas? So data frame person, we read SQL query. You remember this command from the last section. We select all from person, we indicate the connection, select all from grades, and we indicate the connection. Now in Pandas, you have this function called what? Merge. Now, how does merge work? You take your first table, which in this case, based on the old notation, table person is now our what? Our left table. Left table, and grades is our right table. So we say person.merge grades. How do we want it to be merged? Inner. Left on what? So that's merge on the left table. Left person. The person table is the one that has ID. Right on what? The one that has person ID. Can we see how simple it is? By saying we want to merge this to the how? Inner. Left on what? ID. Right on person ID. And then we get this result. Do you understand? That's inner. Now, something that we should note is in Pandas, this merge command is by default always doing the inner join. That's the default, because when we say we want to join two things, it is what they have in common that we should be using to join them, right? So that's the default in Pandas. Now, if we were to use SQL, like strictly carry out this command in SQL, we select all from person and grades, where person.id is equal to grade.person underscore ID. And you establish the connection. Simple. Okay. Let's take a pause. Dolamu. Okay, Dolamu, what is your question? So why doesn't it carry the other data points along? Now, thank you, Oluwaseun, because it is an inner join. Don't worry. If we go back to this chart, what does inner join tell us? Only the things that are common, right? Do you understand? Only what you have that is common. So it is not saying table A has something. Let's put it there now, because I mean they came. No, it is only what they have common that we're going to return. Now, if you're looking for something that is going to return stuff and put a null in the empty values, then the left and right joins are what you're looking for. And we are getting there now. But is inner join clear to everybody, including Dolamu? Okay. So it's like I said, now in who's asking? So Olatunde asked a good question. Now, whenever I say that, whenever we're doing join, so whether in Pandas or in SQL, we are going to carry out a join. The default kind of join um, that gets implemented is an inner join. That's the default. So when you say where person ID equals grades to person ID, like you're literally enforcing it by yourself, saying person ID is equal to grades or person ID. Now, if you want to carry out a left join, now there's a left join. If you wanted to carry out another kind of join, say left join, there's a syntax for it. So you wouldn't use the where clause. Now you could also say select all from person, inner join grades on person ID equals grades the person ID. That's a syntax for inner join as well. But because it is an inner join, you could get away with just using the where clause. Does that make sense? But now if you wanted to carry out a left join or an outer join or the rest of them, you'd specifically include that. But this is inner join. Let's go to the next one, and hopefully it's going to answer your further question. Ianu, you're asking a very interesting question, and we're going to answer that very soon. Just fingers crossed. So now for left join. Now DEF person. So the same thing, but now we want to join on left. We want to join the two tables using the left join, right? So what does that mean? It tells us that we keep everything in our left table, everything that we have, including what is common to both tables. So what does that give us now? Everything in the left table, 6 rows, right? 6 rows. And what you now have that is common, which are rows 5 and 6, they have values. But now the other guys that do not have matching values in the other table, they are returned as null. So Dolamu, do you see that the question you're asking gets answered here when we use a left join to return everything, and then we now have null values? Yes, you're asking, these are valid questions. It is not economical. So what is economical is deliberately specifying the columns that you want returned, right? So you can see that we are using the select star, which is select all. We're just calling everything. These are not large tables, so it's not doing anything to our system. But when you are working on tables with millions of rows, thousands of columns, and you're doing select all the time, then you see the true effect of that on your system's memory economy, right? So if we didn't want to return the person ID, for instance, we could just say select all from person, right? Comma, select all, comma, OnetoOne grade, OnetoTwo grade from person, comma, grades. So that would be in your SQL query statement. Do you understand? You could do that here. Just specify the columns that you actually want, and then it gives you your result. So I didn't print out the results here because this statement is going to give us the same results that we have here. Now, someone asked the question about how does SQL know to do an inner join on where. I've explained that, but you can see that for left join, the where clause is not going to just work on it. You could use the where clause, but then it becomes complex when you have the left join syntax. So you say from person left join grades on person ID equals the grades of person underscore ID. Okay, Olatunde is asking, how do you handle aggregated columns from both tables? Say product is price times inventory. Times inventory quantities in Pandas. So if you wanted to create a new column, so your question is you're creating a new column product, right? So that becomes DF, you open a square brackets, you specify the column name is equal to df.price. So I'm assuming that price and inventory quantity are both columns already existing in the data in that data frame. So product equals df price dot df quantity. When you run that, you're going to see that a new column is created and it has values for your new what's it called? For your new column. Is that clear? There was one question that I didn't answer. So Ianu asks a question saying, does interchanging the left and right table change anything? Then saying left on, right on parameter. Now it's going to change because if ID is not present in the left table, right, then this command is going to fail because it won't recognize ID. It's the same thing. So if you said left on person ID does not exist in your left table. So the command is going to fail definitely. So in that sense, it changes something. But you see this, your first question, which is does interchanging the left and right table change anything? We're going to show you that in right join now. So for right join, you using pandas, the same thing. You just specify how you want to do the join, which is the right join, and you get your result. But now, if you wanted to do it in SQL, so because SQL Light does not have a syntax for right join, what does it do? Or what do you simply do? What you simply do is you flip the position. So you interchange your right and left table. You make your right table your left and your left your right. And then you go ahead to carry out a left join. So that's what you see here. You then select from grades, left join on person, on grades, person ID equals person ID. Can you see? So now the difference between these two tables is grades is coming first in the SQL results and person is coming after. But you see that it's the same set of values. Is that clear? So Ianu, whether this is for what I explained, it applies to left or inner join. As long as it has to be columns that exist in the table. Otherwise, you're asking the table to join another table based on a column that it doesn't have. That is not going to work. It's going to fail. So Fola, okay, thanks. Fola is answering the question that Olatunde asked. Yes, so Olatunde, whether or not the new column is from one table or from an aggregation of the second table, the first thing to know in terms of programming, because this is a programming question, things happen sequentially. There's an order of execution, right? So you want a new column created as an aggregation of columns from two different tables. You could first do your join. The cleanest way to do it is do your join, establish that new column, or establish the join between the two tables, and then create a new column, which you aggregate from there. Or you specify the computation that is going to work there, specify it as a parameter within your merge, and do it on the fly. But the first method that I just explained is better. First, do your join. Once you have the join, you can then pick the two new columns from your resulting join table and then carry out the aggregation from there. That is clear. All right. Then finally, for outer join. Now, for outer join, like I said, the outer join is everything that you have in both tables, right? So unfortunately, SQL Light does not have a syntax for outer join. But again, like I said, you can do it in Pandas, which is specify your tables. How do you want to join them? Outer, left on the column in the left table, right on the column in the right table. And so once you do this, what you realize is you get everything present in your left table, everything present in your right table. Now, where you have matching values, you put them, but where there are no matching values, they are filled with what? Null values, which is like essentially not a number, and so forth. And with this, we have come to the end of today's lecture. Now, simple quizzes before we call it a day. In an SQL left join, which table's data is preserved entirely? You know how we do? Answers in the chat. Thank you. So I see that we're getting the same response. That's left table. So in an SQL left join, like I said, you maintain the entire table, which is your left table, and then include what is common between both tables when you want to add items from the right table. So a flip side of this question is, in an SQL right join, which table's data is preserved entirely, which would be the right table? But for this question, the response is left table, which is correct. And then for question B, what is the primary criterion for joining tables in an SQL query, or in a SQL query? Great. Amazing. Great. Okay, yes, I'm seeing enough answers. Yeah, the primary criterion for joining tables is a common column or key between the tables. There has to be something that you join both of them on. Otherwise, you don't get a possible join. So those were the questions. So now I saw some other questions in the chat. So let me just try and address them. Now, so we can only join using primary keys. For the sake of today's class and what we have learned, that is the ideal situation, right? That is the ideal situation, that you have an ideal case of a table that has a primary key and you're joining it with another table based on the primary key. That's the ideal situation. Then, so left on is the primary key and right on is the foreign key. No, so I wouldn't exactly tag them as such, even though I understand where this is coming from and your sentiment is kind of right, but I wouldn't tag it as left on is primary key and right on is foreign key, because what if the tables were flipped? Then would you then say left on is still primary key and left on is foreign key? No, but all we should just take from this is to know is that whenever you can join two tables based on a key, then the idea is that column was existing as a primary key somewhere, and it is being used as a foreign key elsewhere, to the point where it could be the case that you're joining two tables where that column is an original primary key somewhere, but it is appearing as foreign keys in those two tables that you're joining. Do you understand? The whole idea is from wherever that column originated, it was a primary key. Now, if you're going to be joining based on that column anywhere else, then you're using it as, it's either you're combining the primary key, the table where it is a primary key and the table where it's a foreign key, you're combining multiple tables where that column is appearing as a foreign. Does that make sense now? Do we have any more questions? Great. So that's the end of today's class. Another reminder, please fill our forms, the feedback form, the attendance form, the group preference form. We need your feedback, we need your inputs to be able to do this better. So now we'll be going on our 1 hour break, and we'll be having the lab session. So for instance, I like today's class. It was very interactive, and you guys may not know, but our lab, the person who's going to handle our lab session, our lab tutor, was in the chat, grinding it out with you, giving you solutions to some of the questions. So I can imagine that the lab session is going to be even more interesting. So we'll be expecting to see you there. Fola, you can just give them quick teaser, tell them that you're ready for them, and then we'll see them in an hour.
Hi, everyone. Get ready. I don't know how to tease you, but I know it's going to be very fun and interactive, and you get to try the SQL queries yourself, and we can go in depth into like some of the questions that you have and try different scenarios if you want, even beyond what is already in the lab.
All right, awesome. Yeah, so thanks for